In this segment, I briefly discussed how we evaluate parsing results. So how do we go about evaluating whether our parsers are doing a good job or not? One measure would just be to say, is the parse that we produce exactly the right parse according to the tree bank? That's a possible standard and actually close to what the probabilistic models do, but it's a tough job to get the entire structure of a sentence right, and so the most used evaluation measures have divided up the pieces of a parse so you can get partial credit for being right. So let's go through how that works. So the idea is we start with a gold standard parse tree. This is the correct parse of this sentence. And so then we run our parser, and our parser is going to choose some parse tree for the sentence and return it. So in the example here, the parser is mostly right. It's got the noun phrase sales executives. It's got this verb structure of were examining, and the noun phrase the figure's right. It's actually made one little mistake at the end. So yesterday should be this kind of weird kind of temporal noun phrase that English has, where you have bare noun phrases like yesterday or next week to express a time that can otherwise be expressed as a prepositional phrase like on Sunday in the spring. But the parser has wrongly just stuck it on as an extra noun at the end of the noun phrase great care. And so that's an error. So how are we going to go about measuring that? Well, the way that we're going to do it is we're going to look at individual constituency claims. So here is a noun phrase, and we're going to say that it goes from position 0 to 2 in the sentence, where I'm putting these fence post marker numbers in between the words of the sentence. And so then we look down at our guessed parse and say, well, it also has a noun phrase that goes from 0 to 2 in the sentence. And so that particular constituency claim in the gold tree is correctly captured in the parse tree. And so the way we do that for all the cases is we convert the gold tree into a set of constituency claims, where we leave out the root node, so I've written claims across the root node. So these are our constituency claims. So we have a sentence that's going from 0 to 11, and then the various other constituency claims. Then we do exactly the same thing for the candidate parse suggested by the parser. And so it's also suggested that the whole thing is a sentence from 0 to 11. It's also suggested the NP from 0 to 2, and so on. So it's got a set of constituency claims. And then what we do is we simply treat each of these as a unit, as an atom that you either get right or wrong. And then we use exactly the same precision recall F measure that you've already seen several times before. So here are the gold standard labeled bracketings. Here are the candidate labeled bracketings, and I've shown in bold the 3 that the candidate agrees with the correct parse on. And so in total, there are 8 bracketings in the gold parse and 7 in the proposed parse. So the labeled precision is 3/7, 42.9%, recall 37.5%, and the F1 that combines those in the usual way comes out as 40%. Now, what that partly means is when before we had this, there were these extra nodes down here for the parts of speech that we talked about before. We don't, in the parsing measure, evaluate the part of speech taking, even though most parsers do part of speech taking as part of their work. So that's reported separately, and in the example I've got here, the tagging is completely correct, and so that's 100%. Something that you might notice here is that these scores are actually pretty low, and it's worth thinking a bit about why they're so low. And what we find is that even though the candidate parse was mostly correct, we actually get a lot of brackets wrong. So what happened, the only thing that was wrong in the candidate parse was that this noun yesterday was wrongly fit into this noun phrase rather than being a sentential modifier as a temporal NP. But as a consequence of making that mistake, the parser is scored as doing a lot of other things wrong. So that this verb phrase is scored as wrong because it's wrongly extending to cover yesterday, whereas it shouldn't. This verb phrase is wrong for exactly the same reason. This prepositional phrase is wrong for the same reason, and so is this noun phrase. So this label precision recall measure suffers from these cascading errors whenever you attach something very low that should be high, or vice versa. So many people think this is actually not such a good measure of parser performance, and people, including me, have argued that instead we should use dependency measures of parsing performance even for constituency parsers. But that just isn't the current practice of what you see everywhere in research. The measure that you see is this labeled precision, labeled recall F1. And so that's the measure that we've presented here. I'll just briefly mention, you can also do an unlabeled version of these measures where you simply look at the constituency claim as a sequence of words without worrying about the label, but that's much less used. Okay, so now that we know how to evaluate PCFGs, how well do they do? Well, if you just train a PCFG off the Penn tree bank and run it on some Penn tree bank test data and evaluate with this measure, the answer is you get about 73% F1 measure. So that's not terrible. You get quite a lot of the brackets right, but remember it is counting each bracket separately. So if you're getting over a quarter of the brackets wrong, that means that you're tending to make several bad attachment errors in every sentence. So it's not a great result, and we'll talk about how to improve it very soon. So let's just summarize, though, a little bit the properties of the PCFGs that we've seen up until now. So the good things about PCFGs is that they're very robust. You normally, when estimating a PCFG off a tree bank, you get the result that with smooth probabilities that every possible string of words is included in the grammar. So there's no categorical grammar constraint whatsoever anymore. All the action is in the probabilities, what's high probability and low probability. And that's useful because the parser is robust. You can give it anything at all and it'll do its best job to give you the most likely sentence parse for that. Another good thing about PCFGs is that they give us at least part of a solution to grammar ambiguity. So like in the example of people fishing that I showed earlier, that the PCFG tells you which parse for a sentence to choose, and at least sometimes it chooses the correct one. So it gives some ideas of the plausibility of a parse, but as we'll see more later, and you already got a hint of, that because of the strong independence assumptions of PCFG, it's not actually very good at doing that. A third good property is that PCFGs give us a probabilistic language model, so we can say how likely or unlikely sentences are in a language. But it's important to point out that if you shouldn't just now go and run off and think, aha, I've got a grammar, I'll use a PCFG as a better language model than the bigrams and trigrams we saw earlier. Because actually a PCFG, as we've shown it so far, doesn't work as well as a bigram or trigram as a language model for tasks like spelling correction or speech recognition. And the reason that seems to be is that PCFGs lack the lexicalization of a trigram model. So what do we mean by that? Well, what we meant by that is that if you're looking at this PCFG, most of the PCFG is of the nature VP rewrites as VBD VP, that rules that are expanding without any reference to what words are actually used in the sentence. In fact, the only rewrite rules that consider words are the ones that rewrite from a pre-terminal to the word itself. And so this limits the ability of a plain PCFG to act as a very effective language model. That's a problem we'll address again very soon. But for the moment, you now know how to go about evaluating constituency parsers.